Today we will understand Stokes's theorem in a clear and simple way. Stokes's theorem connects two important ideas in vector calculus. It says that the surface integral of the curl of a vector field over a surface is equal to the line integral of that vector field around the boundary of that surface. In simple words, if you add up all the tiny rotations inside a surface, you get the total circulation around its boundary. That is the core idea of Stokes's theorem. Now let us understand the terms involved. F represents a vector field. S represents an oriented surface. The boundary of S is a closed curve surrounding that surface. Curl of F measures the local rotation of the field at each point. The surface integral adds up rotation over the surface. The line integral measures how much the field flows around the boundary curve. Let us build some intuition. Imagine water flowing over a thin soap film. At each point, the water might swirl or rotate slightly. Curl measures that local spinning. Stokes's theorem says, if you add up all those tiny rotations inside the surface, you get the total flow around the edge. So inside rotation equals boundary circulation. Now let us look at curl in component form. Curl of F is computed using partial derivatives of the components of F. It can be calculated using a determinant involving unit vectors, I, j, and the partial derivatives with respect to x, y, and z. This gives us another vector representing rotation. Now let us see a simple example. Take the vector field F equals minus yx0 and let the surface be the unit disk in the xy-plane. Step 1, compute the curl. When we calculate the curl of this field, we get the vector 0, 0, 2. This means the rotation is constant and points in the positive z direction. Step 2, compute the surface integral. Since curl equals 2 in the z direction and the surface is a unit disk, we multiply 2 by the area of the unit disk. The area of a unit circle is pi. So the surface integral becomes 2 pi. Step 3, verify using the line integral. We now compute the line integral around the boundary. When we evaluate it from 0 to 2 pi, the result is also 2 pi. Both integrals match. So Stokes' theorem is verified. Now let us look at applications. Stokes' theorem is very important in electromagnetism. It appears in Maxwell's equations. It is used in fluid dynamics to study vorticity and circulation. It generalizes Green's theorem from 2 dimensions to 3 dimensions. It is also a foundation for differential geometry. Now, some key properties. The orientation matters. The direction of the boundary must match the surface normal. The result does not depend on the exact shape of the surface. Any surface with the same boundary will give the same answer. Green's theorem is actually a special case of Stokes' theorem, and in higher mathematics it extends to many dimensions. So to summarize, Stokes' theorem says total rotation inside a surface equals total circulation around its boundary. Interior behavior determines boundary behavior. And that is the beauty of Stokes'